Imagine a material so robust, so incredibly resilient that it dwarfs the strength of steel many times over. This is not science fiction, it's the humble spider silk. And here's a fact that blows minds. One strand of this animal's silk is 5 times stronger than steel by weight. Yes, you heard that right. To break a single pencil-thick strand would require 70,000 pounds of force. That's the equivalent of a fully loaded semi-truck. Meanwhile, a human hair is 20 times thicker than the dragline silk a spider uses. Nature looked at steel and said, "Cute attempt." And if you tried to knit a sweater from this biopolymer, mainly composed of protein, you'd be essentially indestructible. It's lighter than air too. A single web covering an entire football field would weigh less than 1 pound. Your own tendons wish they had this property. This super material isn't just strong, it's incredibly light. Even its weakest form, when stretched to its limit, can still manage over 40% elongation. Its molecular structure is a marvel. Spiders inhabit diverse biomes on every continent, from the scorching Australian deserts to humid Amazon rainforests, essentially everywhere except the icy poles. And that strength, it's not just a number, it's a capability. A dragline thread can withstand forces up to 2.7 gigapascals. Your strongest steel cables fail at 1/3 that pressure. Ever wonder how they do it? They produce up to 7 distinct types of silk, each optimized for specific functions. Orb weaver spiders, common globally, construct intricate spiral webs that can be up to 3 feet in diameter, ensnaring up to 90% of local flying insects. Behind every gleaming thread lies a marvel of bioengineering, the spider's internal spin factory, capable of producing up to 7 different specialized silks. Imagine your body trying to build a skyscraper with just one tool. These 8-legged architects boast a full 7. Your fastest industrial processes take 10,000 times longer for similar strength, and they're not even working with liquid protein. Spider glands convert liquid protein into fiber in mere milliseconds, a process so swift it's almost invisible. Each gland contains a specialized recipe of proteins called spideroins, carefully stored. These spideroins undergo a pH shift and mechanical shearing to become silk, a biochemical transformation faster than you can blink. Spiders possess up to 6 different spinnerets, depending on species, each a complex organ for extruding this incredible material. Many orb weavers boast 3 pairs of spinnerets, which are highly mobile, allowing spiders to precisely guide the emerging silk threads. The pyriform glands, for instance, produce a sticky cement silk, enabling secure attachment points. This allows the spider to anchor its web to virtually any surface, from a delicate leaf to a concrete wall. Inside the spinneret, liquid protein undergoes a pH shift from neutral, pH 7.0, to acidic, pH 5.5. Your stomach acid is always just 1 pH, making this feat even more astonishing. This rapid solidification process takes mere microseconds, a biomanufacturing feat industrial engineers still struggle to replicate efficiently. Each major ampulate spigot can extrude a thread up to 20 micrometers thick, providing the primary structural elements of the web frame. The spider carefully lays down these drag lines, sometimes covering several meters in a single strand, creating its deadly aerial ambush. Spider silk boasts an atomic-level blueprint revealing a material science marvel with up to 1.3 gigapascals of strength. The true genius, though, isn't just its production, but that invisible blueprint. Think of it as nature's own carbon fiber, only far more sophisticated. This dual-phase structure is where the magic happens, featuring alternating regions, giving silk absurd versatility. For starters, rigid beta sheet regions, making up 25% of the silk protein, act like microscopic rebar for incredible tensile strength. Then come the amorphous regions, a whopping 75% of the protein, serving as flexible shock absorbers that soak up energy like a pro. It's this delicate balance, the alternating crystalline and amorphous domains, that allows a single strand, just 4 micrometers in diameter, to possess such incredible properties. Evolution had plenty of time to tinker, which is why some silks boast over 1,000 distinct amino acid residues, each fine-tuned for a specific purpose. Consider this, a material 5 times stronger than steel by weight, yet it can stretch a mind-boggling 40%. No wonder early humans were so captivated by this fiber. It can absorb kinetic energy by stretching up to 50% more than its initial length, a feat unmatched by modern engineering. This protein masterpiece is spun under specific acidic conditions, forcing the spidroins into stable, insoluble alignment. And get this, some silks even possess limited self-healing properties, allowing protein chains to reconnect under the right conditions. It's nature's ultimate multi-tool, and we're still trying to catch up. This is the spider's world, built on strands invisible to us, yet stronger than steel. Imagine a single strand, a thread of pure silk, capable of stretching 40% before snapping. Spider silk can indeed be 5 times stronger than steel, a fact that still baffles engineers. This incredible material forms the foundation for their survival, a testament to nature's unparalleled design. Orb weavers, for instance, construct intricate webs that can stretch up to 20 meters, larger than many rooms. When danger strikes, their dragline silk acts as an emergency braking system, a lifeline faster than your reflexes. Young spiders, mere specks, embark on epic journeys using silk for ballooning, traveling thousands of kilometers on the wind, a migration that dwarfs any human trek. Their silk retreats and burrows, reinforced marvels, can last anywhere from 3 to 6 months, providing crucial shelter. And for their young, the egg sacs are masterpieces of protection, ensuring that 9 out of 10 offspring survive. Some spiders even weave silk to manipulate light, their webs reflecting 80% more UV light, a dazzling beacon for prey. Once caught, prey is encased in silk, setting faster than quick-dry concrete. The diving bell spider crafts an entire underwater air pocket from silk, living a subaquatic life. Even trapdoor spiders, lurking just 10 centimeters from their silken thresholds, use silk to ambush unsuspecting victims. Their attachment discs, made of piriform silk, create bonds 3 times stronger than superglue. Bola spiders, masters of deception, mimic pheromones to lure moths from 30 centimeters away. Across South America, communal spiders weave massive silk cities, housing thousands. We humans chase this marvel for medical sutures, investing over $100 million annually. The delicate threads spun by a tiny arachnid hold a monumental promise for humanity's future, inspiring a revolution in material science. Scientists are now engineering biosteel, a synthetic material mimicking spider silk's unique properties, a pursuit ongoing for over 3 decades. This quest, complex as decoding over 1,000 amino acid sequences, has finally begun yielding incredible results. In medicine, its biocompatibility and strength make it ideal for sutures, nerve repair scaffolds, and advanced surgical meshes. The potential for artificial tendons or ligaments is enormous, with early prototypes showing 95% comparable strength to human connective tissue. Your own knee might get a silk upgrade. Aerospace engineering envisions lighter, stronger composites for aircraft bodies, reducing fuel consumption by up to 15% on long-haul flights. Imagine airplanes practically wearing silk. Bulletproof vests and extreme sports gear could integrate silk, offering superior protection at a fraction of current material weight. Why lug around heavy Kevlar? Unlike petrochemical synthetics, biosteel production can be far more sustainable, requiring 75% less energy than conventional manufacturing processes. Producing 1 kilogram of synthetic spider silk uses only 1/10 the energy of steel production. Your factory's power bill just got a serious haircut. Major breakthroughs occurred in 2002 and 2010 with successful gene transfer into goats and silkworms to produce silk proteins. Still, producing synthetic silk on a commercial scale remains cost-prohibitive, with prices exceeding $50,000 per kilogram. It is more expensive than gold, which currently trades around $65,000 per kilogram. Imagine your clothes costing more than solid bullion. Despite these challenges, the immense promise of biomimetic spider silk drives dedicated researchers worldwide, anticipating its transformative impact on future materials. The original spider, meanwhile, continues its quiet, unsung work across every terrestrial ecosystem.